In this video, we'll be talking about the energies of orbits, and the energies of orbits can be described by these two formulas, one for the circular orbit and one for the elliptical orbit. Now, later on in the video, I'll show you how to derive these formulas, because I know some university physics classes probably won't give you a formula sheet for this. So, I'll show you how to make the formula so that maybe if you forget, you don't have to memorize it, you can just make it in the test. Now, let's go ahead and do this problem. You have a green transfer orbit, which is this elliptical one. Find the work of the engine the satellite has to do in order to go from the larger orbit, the larger white ring, and the elliptical or transfer orbit. Now, the reason it's called a transfer orbit is because satellites in real life, they kind of go from a circular orbit to an elliptical orbit to get to this smaller orbit, this inner white circle here. So they have like a orbit in between to, I guess, put less work on their engines or something. Doesn't matter. Okay, let's just solve the problem. So in order to find the work something has to do, well, we need to find some change in energy. So how do we find some change in energy? We have to calculate the energies of the orbits first. Let's go ahead and use our formula. So use our formula for the circular orbit first, and let's find the energy of the larger circular orbit. Energy of the larger circular orbit is the mass of the planet, which is 5 times 10 to the power of 25 times 3 the mass of the satellite, divided by 2 times r, or the distance, or the radius, sorry, of the orbit. So r1 is the radius of the larger orbit, so r1 is equal to 1.5 times 10 to the power of 9 meters. Once you've evaluated this into your calculator, you should get an energy of 3.34 times 10 to the power of 12 joules. So this is the energy of the larger circular orbit. Let's find the energy of the elliptical orbit. Well, the elliptical orbit uses A, which is the semi-major axis. So what's the semi-major axis? Well, the semi-major axis is just the distance from the center of the elliptical orbit to the longer end. So there's two radiuses, two main ones. This is the semi-minor axis, which is the shorter part. The semi-major axis is from the center to the longer end. This is A right here. So how do you find A? Well, in order to find A, we have R1 and we have R2. So we can find the average distance that they cause by adding them and then dividing them by 2 in order to get the length of A. So we can find their average distances, and that equals A. Let's add R1, 1.5 times 10 to the power of 9, plus 1.2 times 10 to the power of 9 over 2. And you should get 1.35 times 10 to the power of 9 meters for A. So now that we have our semi-major axis, we can put them all together. So let's write the equation for the elliptical, the energy of an elliptical orbit. So always there's a gravitational constant somewhere, and we divide it by the mass of the planet times the mass of the satellite over 2a, and a right here is 1.35 times 10 to the power of 9. Well, once you've evaluated this into your calculator, you should get an energy of 3.71 times 10 to the power of 12 joules. So now that we have both of these energies, what can we do? Well, if the larger orbit's the initial and the elliptical orbit is the final, right, the final energy, so change in work is equal to final minus initial energies. So if we subtract the final energy, so the final energy is the elliptical orbit energy, which is negative 3.71 times 10 to the power of 12, and we subtract it from negative 3.34, the initial energy state, or the larger orbit's energy, then we should get a final change in energy, or work, of 3.34 negative 3.66 times 10 to the power of 11 joules. So if your work is negative, that means you resisted against your own movement, which makes sense, right? If you're on a larger orbit and your satellite does work to resist against your current movement, so you're doing a negative work on yourself, then, well, since your velocity slows down, you must approach closer and closer to the planet. So this negative work makes sense here. Let's show you the derivation for the energy of a circular orbit. Okay, so the result we should be getting is negative g big M times little m times 2 over 2r. So where do we start off? Well, you always start off with the universal law of gravitation, which is equal to, which the force of something is the force of a gravitational pull, is equal to g times m, m1 and m2. But since we're talking about orbits, there should be a bigger mass and a smaller mass. So we use big M and little m over r squared. Now, since this is the force of gravity, we can set the force of gravity equal to centripetal force, right? So there's a certain amount of force that you need in order to keep something in a circular motion. So we can set this equal to the centripetal force formula. So mv squared over r. Well, now that we have the centripetal force formula, we can cancel out the bottom r's, and we can cancel out, so this exponent cancels out, and this little masses cancel out. So we get left off with g times m over r is equal to v squared. So using this velocity formula, we can derive that your velocity of something orbiting is determined by the square root of the gravitational constant times the mass of the large object over r. Okay, now that we have this, we understand that your total energy is determined by your kinetic plus your potential energy. Well, your kinetic energy is 1/2 times mass velocity squared. And your potential energy, well, your potential energy is the integral of force with respect to distance. And the force here is determined by your force of gravity. So if you take the integral of the universal law of gravitation with respect to distance, or r, you get negative g big M little m over r. Correct? Well, if you add the potential and kinetic, you get your kinetic energy minus, because you have a negative in your energy, minus g times m, big M times little m over r. Well, we determined that your velocity in order to orbit something is, well, square root of g times m over r. Well, we can substitute your velocity here to get, the square root of g m over r squared. But the square root and the square cancel out, so we get g m over r minus g big M over r. Well, we can expand further, and if we multiply little m and the half into here, we get g big M little m over 2r minus g big M little m over r. Well, if you multiply this by 2 over 2, which is just equal to 1, and in doing so, you get the same denominators. So in order to add fractions, you need the same denominator. So you get minus 2g big M little m minus 2r. So if you subtract these two from each other, you get the result of negative g m little m over 2r. And this right here is the formula for your energy of a circular orbit. Now, if you want to find the formula for a elliptical orbit, literally just replace, I'm so serious, just replace r with a, the semi-major axis length. So that derivation isn't too bad. You just use some logic about centripetal force and total energy. But as always, if you have any questions, put it down in the comment section. And if you think that this video helped, consider subscribing and liking the video. Thanks for watching.